That was going to be the other thing. I was going to ask you to record. Thank you.
Yeah.
I mean, if you don't have it, you don't have it. I mean, that's.
Well, I'll make sure that if I haven't recorded it, I certainly have the slides.
Oh, okay.
So I will post them on. I will post them.
Thank you.
Okay.
Can I get please a clarification for problem set 3, number 5? It says compute the cardinality of the solution sets in the real numbers and the complex numbers of the following polynomial equations. That is just, I mean, you're asking us to solve those equations and report how many solutions there are. Is that correct?
Yes.
Thank you.
So are there any questions? If not, I'll just review some of the newer material.
Yes, I have some questions. I'm sorry.
Okay.
Can you go over 1.3, number 6?
In what section?
Section 1.3, question 6. It has to do with relations and proving that the given relation is reflexive, symmetric, transitive, and then constructing the complete set of representatives for the relation.
Let me just. Okay, here's section 1.3. And
Question 6, please.
okay, this is where m is a positive integer? Is that how it starts? So I think what you're asking about is the following question. It says m is a positive integer, and we define a relation on Z as follows. A is related to B if M, or that's right, well, A or B or X or Y doesn't matter. If M divides A minus B. And we want to prove this relation is reflexive, symmetric, and transitive. Is that the question you're asking about?
Yes, it is. Thank you.
Okay. So this is exactly the definition of congruence. So, which is the subject I started to talk about in the last 2 lectures. We say that A is congruent to B modulo M. So this is what we are defining if M divides A minus B. So I claim this relation is reflexive, symmetric, and transitive. So for all integers A minus A is 0. And 0 is M times 0. So M divides A minus A. So A is congruent to A mod M. So in this relation, everything is related to itself. This relation is reflexive. Why is this relation symmetric? So that A and B be integers. So then we have the following sequence of implications. If A is congruent to B mod M, that means M divides A minus B, which means A minus B is M times Q for some Q. And if you multiply by -1, b minus a is minus mq, or m times minus q, which means m divides b minus a, so b is congruent to a mod m.
Oh, you did this in lecture 6, didn't you?
I've done it a couple of times, yes.
Okay, thank you.
All right. So this is the proof that this relation is symmetric. And why is it transitive? Suppose A is congruent to B mod M, and B is congruent to C mod M. So this means that A minus B is M times some number Q. And this means that B minus C is M times some number T. If we add these equations, the B's cancel. A minus C is MQ plus MT, which is M times Q plus T. So M divides A minus C. So A is congruent to C mod M. So this relation, which I defined in section 1.3 and comes up again in chapter 3, is the relation of two integers being congruent modulo M. And this relation is reflexive, symmetric, and transitive. So that means it is an equivalence relation. That's the definition. And what is a complete set of representatives for this relation? So for every integer a, by the division algorithm, if you divide a by m, you get m. A is equal to m times some quotient plus a remainder, where the remainder is between 0 and m minus 1. So a minus r is mq, which means a is congruent to r mod m. So every integer is congruent to r modulo m for some r between 0 and m minus 1. I claim that these numbers between 0 and m minus 1 belong to different equivalence classes mod m, so that r and s be any two numbers between 0 and m minus 1. Suppose r is congruent to s mod m. That means r minus s is m times q for some integer. So the absolute value of r minus s is m times the absolute value of q. Suppose this q isn't 0. Well, let me put it like this. If q isn't 0 and it's an integer, then the absolute value of q is at least 1, and the absolute value of r minus s, which is mq, is at least m. But here's our picture. We have the integers from 0 to m minus 1, and r and s are in this interval. But the absolute value of r minus s is at most m minus 1. So it can't be greater than or equal to m and less than or equal to m minus 1. So therefore, q has to be 0. R minus s equals 0, r equals s. So this means that no two integers in this set are congruent minus modulo m. So the set 0, 1, 2, all the way up to m minus 1 is a complete set of representatives for the congruence relation. Okay. That's very important. Are there any questions about this? Okay. So we have these congruence classes. So what is the equivalence class of A mod M? So we call that a congruence class. So the congruence class of A modulo M, this is the set of all integers B such that A is congruent to B mod M. Let me write it the other way. It doesn't really matter, but slightly more convenient. All integers B, which are congruent to A mod M. So this is all integers B, such that B minus A is a multiple of Q for some Q. This is the set of all integers you can write in the form A plus MQ, Q and Z. And our notation for this is A plus MZ. So this is really an arithmetic progression. This is A plus Q, A plus 2Q, A plus 3Q, A minus Q, A minus 2Q, A minus 3Q. It's an infinite arithmetic progression. This is the congruence class of A. This is an equivalence class of this relation. And there are M different congruence classes. So we have 0 plus MZ, 1 plus MZ, 2 plus MZ, and minus 1 plus MZ. Here we have M sets of integers, and they form a partition of the integers. We denote this by Z slash or mod MZ. That's the notation. This is the set of M congruence classes modulo M. So this is extremely important. That's going to be our basic example for many other concepts in algebra. MZ, or the congruence class of 0, is just the multiples of M. Let's look at an example. Let's take M equal 2. So the congruence class of 2, which I just write as 2Z, this is all multiples of 2. What is that? This is just the even integers. The congruence class of 1 is just 1, 3, 5, 7, 9, minus 1, minus 3, and so forth. This is just a set of all odd integers. So if you look at Z mod 2Z, this just consists of two sets, 2Z and 1 plus 2Z, or in other words, the evens, the set of even numbers, and the set of odd numbers. So if you take just the modulus M equal to 2, you get something you've known since elementary school, that every number is even or odd, and you have the set of all the even numbers and you have the set of odd numbers. Those are the two congruence classes of this relation. Are there any questions about this? Now, An important fact about congruences is that you can add them. So we have the following simple facts. If suppose A is congruent to A prime mod M, and B is congruent to B prime mod M. So this means that A is A prime plus a multiple of Q, and B is B prime plus a multiple of M, and B is B prime plus a multiple of M. If we add these equations, we get A plus B is A prime plus MQ plus B prime plus MT. This is A prime plus B prime plus M, Q plus T. So this means that A plus B and A prime plus B prime are congruent. So if you have two congruences, you can add them. And what happens when you multiply A and B? A times B is A prime plus MQ, B prime plus MT. This is A prime, B prime plus M, B prime Q plus M, A prime T plus M squared QT. This is A prime, B prime plus M times B prime Q, A prime T, MQT. This is some integer. So by multiplying, we see that AB is congruent to A prime, B prime mod M. So you can add and multiply congruences. These are true, correct, reasonable, well-defined mathematical operations. And from this, we can define addition of congruence classes. You have the congruence class of A plus MZ and the congruence class of B plus MZ. The sum we can define to be the congruence class of A plus B plus MZ. So this congruence class plus this congruence class added together we define to be this. And we can define multiplication A plus MZ times B plus MZ is AB plus MC. And you can check in the notes or in the lecture I posted, or it follows from exactly the calculation here, that this is well defined. It doesn't matter what choice of representatives of the congruence class you take. So for example, we take M equal to 3, we know that 17 is congruent to 29 mod 3. And minus 8 is congruent to 16 mod 3. You might want to check that this is true. So if you add, you get that 9 is congruent to 45 mod 3. And if you multiply, what is 8 times 17? I don't know, 8 sevens are 56. 8 times 1 is 8 times 5 is 13. So minus 135 is congruent to whatever you get when you multiply these two numbers together. What is 29 times 16? 30 times 16 would be 480, but you have 116 too many. So let's try 464 mod 3. Is that right? Let's see. 30 times 16 is 480. So 2916 is 464. 8 sevens are 56. Yeah. Yeah. So this should be a true congruence. Yeah. Now, what are some properties of addition and multiplication of congruences? So we know how to add numbers. And we know how to add now congruence classes. Addition of integers is associative. So for any integers x and y, x plus y plus z is x plus y plus z. And you can check that the same is true for addition of congruence classes. X plus mz plus y plus mz. Take these two congruence classes and add them together and add z plus mz. And you get x plus mz plus y plus mz plus z plus mz. And it just follows from the definition of addition. In the integers, you have the existence of an additive identity. It's 0. X plus 0 and 0 plus x is 0. So the identity, the additive identity, is 0. In the congruence classes, you also have an additive identity. It's just the congruence class 0 plus mz or mz. Because if you take x plus mz plus mz, or mz plus x plus mz, you get x plus mz for all x. So the congruence class of 0, the set of all multiples of m, is an identity in the set of congruence classes mod m. And we also have the existence of an additive inverse. Namely, for any integer x, there's an integer minus x, and x plus minus x and minus x plus x is 0. And for congruence classes, if I take the congruence class of x and I add the congruence class of minus x, that's the same as the congruence class of minus x plus mz and the class x plus mz. And that's still equal to 0 plus mz. So here, minus x is the inverse. Here, minus x plus mz is the inverse. And there's another property that congruences satisfy just as integers do, which is called commutativity. x plus y is equal to y plus x for all integers, and x plus mz plus y plus mz is equal to y plus mz plus x plus mz for all integers. So this is the commutative property of addition. So this is extremely important. The integers z in the congruence class of z mod mz are two examples of additive abelian groups. So let me say, what is a group and what is an abelian group? So you have a set with a binary operation. A binary operation like addition or multiplication is given any two numbers, you can use them. There's some operation that gives you a third. So for addition, if I give you 7 and 5, addition gives me 12. Multiplication is another binary operation. If I give you 7 and 5, multiplication gives 35. So this is the definition of a group in algebra. So the group has to have a binary operation which is associative. There exists an identity. And every element has an inverse. So if the group is additive, or if the group is multiplicative, the same properties have to hold, but we just write them differently. So if the operation in your group is additive, the associative property means x plus y plus z is x plus y plus z. And if our operation were multiplication, it would be xy times z is x times yz. If the group is additive, we call the identity often 0, and 0 is an element of the group with the property that 0 plus x and x plus 0 equals x. In a multiplicative group, we often use 1 to denote the identity. 1 times x, x times 1 equals x. To say every element has an inverse means for all x, there exists a y such that x plus y and y plus x equal the identity. Or in the multiplicative case, x times y and y times x equals 1. So the integers have this property. The congruence classes have this property. If you look at the non-zero fractions, they have this property. That's a multiplicative group. Now, some groups, like the integers, have an additional property, which is commutative. So anything that satisfies these three properties is a group. The commutative property would say additively x plus y is equal to y plus x for all x and y, or xy equals yx for all x and y. So a set with a binary operation satisfying properties 1, 2, and 3 is a group. A group that satisfies property 4 is called a commutative group or an abelian group. So ample examples of an abelian group are the integers and the congruence class is mod m. What's an example of a group that is not abelian? So everyone should know what is a 2 by 2 matrix. So let's consider all 2 by 2 matrices, A, B, C, and D, where A, B, C, and D are integers. And the determinant, AD minus BC, is 1. So the set of all 2 by 2 matrices with integer coordinates and determinant 1. I'll call that SL2Z. The 2 stands for 2 by 2 matrices. It's 2. The Z is because the elements are the entries are integers. You see, L stands for linear because these matrices come up in linear algebra, which is something you're supposed to have taken. But in any case, you've probably seen 2 by 2 matrices. S is special. These are special because the determinant is 1. Now these form a group. So this is a multiplicative group. And what is the identity? I'll write it as capital I. It's the matrix 1, 0, 0, 1. Suppose I take some matrix X, like, I don't know, 7, 2, 3, 1. So for this matrix, the determinant, 7 times 1 minus 2 times 3 is 1. So X is in this set. What's another matrix in this set? I don't know. Minus 5, 3, 2, minus 8. What is the determinant of this? Let's see. The determinant of Y is minus 5 times 3 minus 2 times minus 8. This is 15, minus 15 plus 16 is 1. So both of these matrices are in my group. These are matrices in SL2Z. Let me multiply them. 7, 2, 3, 1, minus 5, 2, minus 8, 3. This is minus 35, minus 16 is minus 51. 14 plus 6 is 20. Minus 15 minus 8 is minus 23. 6 plus 3 is 9. Let's see. What is that determinant? So the determinant of xy is minus 51 times 9 minus 20 times minus 23. So this is minus 459 plus 460, that's 1. So this is an SL2Z, of course. Here, the product of two matrices is determinant, and one has a determinant 1. Suppose I multiply in the opposite order. This is minus 35 plus 6 is minus 29. Minus 10 plus 2 is minus 8. Minus 56 plus 9 is minus 47, I think. And minus 16 plus 3 is minus 13. What is the determinant of yx? Minus 29 times minus 13 minus minus 8 times minus 47. Let's see. This is, what is 29? This is positive, 29 times 13. 30 times 13 would be 390. And that's 113 too many, so that's 377. And 8 times 47, 8 sevens are 56. This is, 377 minus 37, this is also 1. So both of these matrices are in SL2Z, but notice this matrix and this matrix are different. XY is different from YX. So SL2Z is a non-abelian group.
Professor,
Yeah.
Can you go back to the previous page? I think I have a question on something that you wrote with regard to groups.
This is the previous page.
Yes. Did you state that Z was a group for multiplication?
No, it's not.
Okay, that's okay. I
No.
was looking, I copied something down incorrectly. I'm sorry. Go ahead.
Okay. Okay. So this group, SL2Z, is extremely important. It's a beautiful example of a group. It comes up in many different parts of mathematics. You've certainly seen it without calling it a group, perhaps, in linear algebra. And it's not abelian. But this is one of the first things you learn about matrices. Matrix multiplication is not abelian.
Professor, isn't that the same as vector algebra as well?
Sorry?
It's similar to vector multiplication, right?
There is no vector multiplication. Except if you take Calc 3, you learn about the cross product of two vectors, but that's only true for vectors in 3 dimensions. We don't have a way to multiply vectors in general. That is, you never learned anywhere in calculus or linear algebra how, if I give you 2 vectors, how to multiply them and get another vector.
I meant cross product, so yes, you're right.
But that's just for 3 dimensions. And this multiplication of 3-dimensional vectors, it doesn't have any of the properties we would like to make the set of 3-dimensional vectors a group. It's not commutative, it's not associative, there's not an identity. It's a very important thing in geometry and in physics and in calculus, but it doesn't give you a group structure. But since someone just mentioned the integers and multiplication, it is true. We can multiply the integers. And multiplication of integers does have some very nice properties. First of all, it's associative. For any 3 integers, x, y times z is x times yz. There is a multiplicative identity, which is just the number 1. 1 times x and x times 1 is always equal to x. But you don't have an inverse. There's no inverse of 2 in the integers. There is in the rationals, but not in the integers. But you also have a distributive law, which is the following. If you have integers x, y, and z, x times y plus z is xy plus xz. Oh, and there's one other property, which is this commutative, xy equals yx. Now, it turns out you have similar properties in the congruence classes z mod mz. Multiplication is associative. If you have x plus mz times y plus mz, and you multiply that times z plus mz, that's exactly the same as x plus mz times the product of y plus mz times z plus mz. So multiplication of congruence classes satisfies the associative property. If you take the congruence class 1 plus mz and multiply it by any congruence class, or also in the reverse order, m plus mz times 1 plus mz, you get x plus mz. So the congruence class 1 plus mz is a multiplicative identity in the set of congruence classes. And these other two properties also hold. And the integers and the congruence classes mod m are not only examples of additive abelian groups, but they're also examples of something called a ring. So a ring is an additive abelian group with a multiplication operation that is associative, has an identity, and satisfies the distribution law, has the distribution property. A commutative ring is a ring in which multiplication is commutative. And the integers z and the congruence classes z mod mz are examples of commutative rings. So there are three basic structures in algebra: groups, rings, and fields. So we've defined a group, we've defined a ring, and pretty soon we'll define a field. And that really is what we study in algebra. But the basic examples are the integers and the congruence classes. Let me just give one other example of a ring. Suppose we let's say M2 of Z be the set of all 2 by 2 matrices with integer coordinates. So this is all matrices A, B, C, D, where A, B, C, and D are integers. So how do we define addition of matrices? We define it coordinate-wise. A, B, C, D plus E, F, G, H. You just add the first coordinates, the second coordinates, the third coordinates, and the fourth coordinates. This is an addition. You have 2 matrices, you add them, you get another matrix. And this addition is associative. What is the additive identity? It's the matrix with all zeros. What is the inverse of a matrix A, B, C, D? It's what you add to A, B, C, D to get the 0 matrix. And this is just the matrix minus A minus B minus C minus D. Add these two together, you get a matrix with all zeros. And addition is commutative. Yeah. And matrix multiplication is defined in the usual way. And with the ordinary addition of matrices and multiplication of matrices, this is a ring. So M2 of Z is a ring. And I left a space because we already saw that multiplication of matrices is not commutative. So this is a non-commutative ring. Any questions about this? So these are concepts which you have to become extremely familiar with. Because in a day or two, all we're going to talk about are groups and rings. There are no more integers. There are no more numbers in this course, really, except as examples. Okay. Any questions?
Yeah. Can you go over a couple of the problems from the homeworks? Do we have time for that?
Yeah, well, we have a problem. Yeah, give me a problem and I will try to do it.
Okay. Homework 2.1, number 6A. And the second part, basically, it asked us to find 2.2. Hang on one second, I'm sorry. Where did I put 2.2? There it is. That's not it. I'm sorry, it's 2.1. I apologize. In A, it asks us to compute the greatest common divisor of three numbers, which I was able to do, but then it asks to find, express it as a linear combination. In the next question, we use the Euclidean algorithm to find the greatest common denominator and then write it in terms of a linear combination. For 2, I could use the Euclidean algorithm, but I wanted to know how you write 3 numbers as a linear combination using the greatest common divisor.
Well, that's a good question. So this is
the second part of 2.1, question 6A.
okay.
6A says compute. I'm sorry. Yeah. It says compute the greatest common divisor of 78, 182, and 273, which I did by right. Okay. 78, 182, and 273. And then once you find the greatest common divisor, express it as an integral linear combination of those 3 numbers.
Mm-hmm. Well, let's see. There are different ways to do it. Let's try one way first. Just to find the GCD. You could just factor the numbers. So 78 is 2 times 39, which is 2 times 3 times 13, I believe.
Yes.
182 is 2 times 91, which is 2 times 7 times 13, I think.
Yes.
And 273, what is that? If you divide it by 7, you get 7 into 27 goes 3 times, 7 into 63 goes 9.
3 times,
so this
3
is
times 7 times 90.
3 times 9.
13.
What?
3 times 7 times 9, yes.
3 times 7 times 9.
Well, 3 times 3 times 7. Is that right? No.
No,
No,
it's
it's
3
that
times 7 times 13.
Professor, 13 has to be a factor.
Just a second. Just a second.
Thir-
So
13 times 7 times 3.
7 into 27 goes 3 times. 3 times
Professor, it's
39.
7 is not.
So this is
Yeah.
3 times 7
7 times 13.
13. Okay. So if you look at this, you see that the GCD is equal to what? 13.
13.
Okay. So that's the GCD. Now, if you want to write it as a linear combination, there are different ways to do it. One way might be you say, okay, first I'll find the GCD of 78 and 182. I can do that using the Euclidean algorithm. And then I can
Yes.
take that GCD and find the greatest common divisor of that with 273. And I will have the greatest common divisor of the three numbers is a linear combination of, if you actually write everything out, you will get a linear combination of these three numbers. Let me just do it quickly if I can. So suppose I want to find the GCD. I take 182, and this is 78 times 2. And what's the remainder? This is 176, is that right? Plus 6.
Yes, sir.
78, if you divide it by 6, this goes in 12 times. No, it goes in
13 times.
exactly 13 times.
Mhm.
So the GCD is 6, and 6 is equal to 182 plus 78 times minus 2. Now, suppose I want to find the greatest common divisor of 6 and 273.
Professor, the
So-
remainder on the first line is 26, not 6, I believe. Isn't
Yeah,
that correct?
exactly, Professor. It doesn't make sense because we know GCD is 13, so it doesn't make sense.
But just forget what we know. I would just want to do the arithmetic right. So 2 times 78 is, sorry,
156.
156.
156. So
Yeah,
the
so-
remainder is 16.
26
The remainder is 26. Okay. Whatever it is what it is. So 78
is 3 times 26 now.
is 26 times 3. Exactly. Okay, very good. So 26 is 182 times 1 plus 78 times minus 2. Now, what about the greatest common divisor of 273 and 26? So if you divide 26 into 273, that goes 10 times and leaves a remainder of 13. And 26 is 13 times 2 and leaves a remainder of 0. So 13 is 273 times 1 plus 26 times minus 10. But 26, so this is 273 times 1 plus, what is 26? 26 is 182 times 1 plus 78 times minus 2. So it is this times 10. So we
Can
get
you move the sheet up,
270.
please? Can you
What?
please move the sheet up? Move the sheet up. Thank you. Thank you.
Yep.
A little farther.
So this is 273 times 1 plus 182 times 10 plus 78 times minus 20. So if the arithmetic is correct, this is a linear combination. This is 13 as a linear combination of the three numbers. If the arithmetic isn't correct, then we go back and correct it. But this method works.
Thank you.
Okay.
One last brief question. You don't have to do any calculations. On homework 2.1, where you ask us to compute the positive divisors of any number, when we break that number into the product of primes, we end up with 2 raised to the power of the number of primes that we have there as the number of divisors. So is there any quicker way?
No. It's actually bigger than that.
Okay, well then I gotten that question incorrect. As an example, you asked us to find the positive divisors of 210. 210 ended up being 2 times 3 times 5 times 7. So I figured there were 16 divisors because to find a divisor.
In that case, that's correct. And the reason it's correct is because the number 210 is a product of distinct primes. It doesn't involve a prime to any factor. If you had a prime to a higher factor, you would have more divisors.
Right. Okay. My main question is, when we get something, let's say that's got 5 primes in it, that's got 32 divisors. To come up with the actual divisors, is there any better way than just multiplying out all the combinations of numbers?
No.
Okay, thank you.
Okay.
I didn't waste my time then. Thank you.
Bye.
Bye.
Professor, one question. In the chapter 3.1, etc., I just want a clarification. How do you prove if something is a complete set of system modulo M? Are the 2 requirements basically it has to have M elements and they have to be disjoint?
Not disjoint. They have to be, well, the congruence classes have to be disjoint. The set of representatives means you have M numbers and no 2 of which are congruent to each other.
Sorry, that's what I meant. So no 2 are congruent to each other. So, and can you, let's say you want to show some system is equivalent to another, all you have to show is that, it has the same number of elements and same number of elements as M, and they are not congruent. Is that what basically it is?
Yes.
Okay.
Okay. Bye, all.
If you have them, could you please post the sheets from last Thursday afternoon? Thank you.
All right. Bye.
Bye.